The sea, a vast, secure and sustainable resource of energy, underused and underexploited. Wave and tidal technologies are at the forefront of renewable energy development. And although there is a constantly replenished resource, it is yet to be fully exploited, as the technologies must overcome many challenges if they are to become economically viable. To help meet UK government energy targets, the Energy Technologies Institute's role is to bring together engineering projects that develop affordable, secure and sustainable technologies to help the UK address its long-term emissions reductions targets, as well as delivering nearer-term benefits. In recognition of this, the ETI commissioned the Performance Assessment of Wave and Tidal Array Systems project, known as PerAWaT. The project aimed to develop and validate numerical models capable of accurately estimating the energy yield of major wave and tidal stream energy converters, known as WECs and TECs. Crucially, it aimed to find out how these energy converters operate together in arrays. Deployment of these large-scale arrays can only occur when investors and project developers have sufficient confidence in the return on their investment. This will require proven prototypes and validated methods for the prediction of resource and energy capture. And this is what the PerAWaT project has aimed to achieve over the 4-year period. £8 million has been invested into this project by the ETI, and it has been delivered by a world-leading consortium spanning academia and industry, headed by DNV GL and including E.ON, EDF, Queen's University Belfast, the University of Edinburgh, the University of Manchester and the University of Oxford. So what exactly is the PerAWaT project? David Clark, CEO at the Energy Technologies Institute, recognised a need for further renewable energy projects.
The PerAWaT project really looked at two aspects of marine energy. It looked at improving the models we've got for individual devices, for both wave converters and tidal energy converters, and then critically it looked at how we implement those kind of products as arrays of devices. And the array is the real thing that the project developers and the investment community want to get involved in. So we've now got the models for good arrays, and we can see a route to improving array efficiency by something like 5 to 10%. Where do we go next with it? Well, now we're in the process of trying to roll this out into the community, and we're trying to now get real sea test data, which is going to really help us understand those models further and give us the confidence and give the investors confidence in using them in anger on real projects.
The world has a significant wave energy resource, which, if properly exploited, could contribute significantly to global energy requirements. Deployment of wave energy converters, or WECs, in pre-commercial arrays is starting to occur now, with many more planned for the coming years. However, there is a need to understand the issues involved and be able to quantify any potential impacts of WECs when operating in arrays. As arrays grow in size, there will be a requirement to carefully consider the planning and analysis of WEC arrays. This is where DNV GL's WaveFarmer software can help. WaveFarmer is a single software tool that allows information from multiple sources to be loaded, simulated and explored. It can accurately calculate the annual energy yield, reducing uncertainty in the cost of energy calculations for technology and project developers, investors and other key stakeholders. Andrew Garrod has had over 30 years' experience in the renewable energy field.
WaveFarmer is a virtual wave farm. So you can imagine a wave farm in real life, devices being put into the sea. And what we're trying to do is to develop a tool which can predict exactly how all those devices will behave, both individually and collectively as a farm.
R.V. Ahilan, Director of Division at DNV GL Energy Renewables Advisory, has been pivotal in the consultancy of the PerAWaT project.
Once you put multiple devices, waves are reflected, diffracted from the single unit, and that can then affect the other units that are on location. So one of the key developments that we've made in WaveFarmer as part of the PerAWaT project is the fact that we are able to calculate rigorously the interference effects between multiple devices, which is an absolutely essential part of being able to identify the energy production capability of a farm as opposed to a single device.
So it's a mathematical model turned into a computer model which allows you to do all the things that you could do very, very expensively in real life virtually on a computer. So it models all the different aspects of a real wave farm, but it does it in a computer rather than in the sea. And therefore it's a lot cheaper and more cost effective and allows us to look at lots of different variations of a farm. So maybe we want to look at the deployment of these devices in different ways, in different shapes, in different sizes, and we can do all of that computationally and therefore reduce the risks of full-scale deployment.
What we have seen from that validation is that the known diminishment of the energy prediction from an array as opposed to a single device was well predicted, very accurately predicted when compared to measurements. So we know that we have some good validation data.
Inputs like seabed elevation, WEC locations, wave inputs, site constraints, and WEC description can be loaded in a wide range of commonly used formats and coordinate systems. WaveFarmer can be used with any type of WEC, including attenuators, pitching flaps, and point absorbers. There is a link to the single WEC design tool, WaveDyn, as well as DNV GL's wave climate analysis and processing tools. WaveDyn has been commercially available through DNV GL since 2012 and was the first public outcome of the PerAWaT project. Energy yield results are broken down graphically by device and sea state to allow in-depth analysis. The genetic algorithm optimization computes the best layout of WECs for you, maximizing yield subject to realistic constraints such as minimum spacing and inclusion or exclusion zones. Maps show geographical information transformed to a single coordinate system and overlaid with results such as modifications to the wave climate from the array. Further extensions and modules are being created as part of DNV GL's ongoing development program. Tidal motion is predictable, offering both a renewable and dependable source of energy. Tidal is a thriving industry that could grow rapidly with investment over the coming decades. The tidal industry is at a point where demonstration farms are being planned. These farms mark the dawn of a new era of marine energy, and the industry now requires tools and standardized methods to help project developers and energy analysts plan arrays which will provide greater confidence to lenders and investors. As arrays grow, there will be a requirement to provide tools and methods that can model their interactions. This is where DNV GL's Tidal Farmer software can help. What is Tidal Farmer? Tidal Farmer is a software tool that allows a user to define inputs to plan and build an array of tidal stream turbines. It models the array interactions within the environment and can predict the potential energy yield, allowing users to quantify uncertainty and make informative investment in the tidal stream industry. But why do we need tools like Tidal Farmer?
Tidal Farmer works by setting up, first of all, a model of the individual device. So we have a device, one tidal turbine. And we understand how that works. And we put that in a tidal stream, so the water passes by the tidal turbine. But of course, if this is going to be something which is commercially attractive and is going to make a large-scale contribution to our energy mix, which I believe it will, then we're not really just interested in how a single tidal turbine works. If water flows past a tidal turbine, it comes to the turbine with kinetic energy, with energy by virtue of its motion. Energy is then extracted by the turbine, and the water has therefore to go slower when it's gone past. If you try to slow it down too much, then actually it looks like a blockage in the river or in the stream, whatever it is. And the water will just say, actually, I'm not going to come here anymore, I'm going to go somewhere else. So you have to be very careful that you don't try and extract too much energy so that the water says, yeah, I can find an easier route some other way. And that's the point of Tidal Farmer.
What Tidal Farmer does is that we are able to model the collection of turbines and figure out how to optimize their locations. Where we've been focused in developing the Tidal Farmer software is to try to account for that wake interaction effect, but actually make it possible in a practical timescale, as opposed to solving the question always from a fundamental perspective. So what we have done in the Tidal Farmer is to take advantage of some of the fundamental calculations in their full detail and their full prediction, and then find the simplifications that then make it practically useful in our industry.
Tidal Farmer has many features that help to accurately predict the performance of device arrays. This includes a recently developed three-dimensional wake model that allows a full realization of a wake downstream of devices. Information concerning tidal stream turbines within a project can be modified, such as the power curve, rotor diameter, and yaw strategy, to help evaluate turbine design concepts. Turbine wakes can be visualized, enabling regions of high velocity deficit to be identified. Graphing tools allow users to view the energy production per device, so that any issues can be identified and corrected. Fast engineering models enable quick design iterations and allow you to quantify the level of uncertainty in a tidal farm project. Maps showing geographical information allow for results to be overlaid, enabling users to explore the impact of an array. Lastly, further extensions and modules are being created as part of DNV GL's ongoing development program. As energy demand rises and the problems associated with conventional generation become ever more apparent, we need to address the serious challenges facing our energy supply. What insights can the PerAWaT project provide to help us in the future?
PerAWaT's a key element of our portfolio for helping de-risk projects for investors in the future. And we see this alongside our device development projects with a number of major industrial groups and our other modelling projects, both for tidal arrays and for tidal modelling around the UK waters as well. But the entire portfolio is focused on increasing investor confidence, and we'll be taking that forward now, looking at future low-cost array developments. Where do we go next with it? Well, now we're in the process of trying to roll this out into the community, and we're trying to now get real sea test data, which is going to really help us understand those models further and give us the confidence and give the investors confidence in using them in anger on real projects.
The ETI's mission is to accelerate the development, demonstration, and eventual commercial deployment of a focused portfolio of low-carbon energy technologies. Projects like PerAWaT play a crucial part in this, helping to promote the use of affordable, secure, and sustainable marine technologies that will reduce greenhouse gas emissions and therefore achieve our energy and climate change goals. DNV GL will be launching WaveFarmer and TidalFarmer early in 2014. For further information, contact WaveFarmer at dnvgl.com or TidalFarmer at dnvgl.com.